In this lecture, I'd like to focus on some of the natural forces of climate change, and they revolve around the idea that the Earth orbits the Sun, and there are many small changes in how the Earth goes around the Sun that affects climate. Keep in mind that these changes in climate are on the 10,000 to 100,000 year scale and would have nothing to do with the most recent changes that we're seeing in climate over the last couple hundred years. So to begin with, there are two fundamental motions that describe the Earth's present orbit around the Sun. First, the Earth spins on its own axis once a day, bringing different regions of the Earth in and out of the portion of the Earth's surface that receives the Sun's radiation. And that describes why we have night and day. The second basic motion is that once a year, the Earth orbits around the Sun. So these describe the two main axes of movement of the Earth around the Sun, its rotation and its revolution around the Sun. These orbital scale forcings are also called the Milankovitch cycles, and the idea behind this is that climate is affected by the way in which the Earth orbits around the Sun. And there are three main parts of how the Earth orbits around the Sun that influence climate. One is precession, the second is obliquity, and the third is eccentricity. And these are now generally accepted as the primary pacing mechanism for the glaciations and the interglacials that we have seen over the last 2 million years. And the way the Earth moves around the Sun and the small variations in that movement are caused by the gravitational pull of the Sun, the Moon, and some of the planets and their moons on our Earth. This orbital theory of the ice ages relies on three dominant pacemakers of climate change. The first one is eccentricity, and that has to do with small changes in how the Earth orbits around the Sun and the shape that orbit makes. And that cycle is about 100,000 year cycle. And I'm going to go into detail of each one of these. The second is the way that the Earth's axis of rotation is tilted, and that operates on a 40,000 year cycle. And the third is much more complicated, but that's basically it's a wobble in the Earth's rotational axis, and that is on a 23,000 year cycle. So the first thing to note is none of these have the same cyclicity. And all of these cycles, all three different components, influence the amount of solar radiation that strikes the different parts of the Earth at different times of the year. But one fundamental idea behind when the Earth experiences a glacial or interglacial, glacial meaning a cold phase or interglacial meaning a warm phase, the key to building up an ice sheet and then creating a glacial age is not necessarily the temperature during winter, but it's the temperature during summer. To build up an ice sheet like the Greenland ice sheet, which you can see there on the left, you need relatively cool summers, which enable any sort of persistent snow cover to remain throughout the summer. So winter temperatures are important, but basically you want cooler summer temperatures, and they would increase the likelihood of building an ice sheet and causing an ice age. The ideas that I'm going to go over today are called Milankovitch cycles, and they're named after Milutin Milankovitch, who lived from 1879 to 1958. And he was a Serbian mathematician that formalized the theory that orbital changes of the Earth were related to changes in climate during the last 2 million years, which we call the Quaternary. And he made these calculations while he was under house arrest and captivity during World War II. And these ideas were a refinement of ideas that were put forth much earlier by James Kroll, who was a Scottish natural historian. Milankovitch basically said there are three important parameters of how the Earth orbits around the Sun. First is the shape that the Earth makes. The second is how much tilt is there in the axial plane. And third is the amount and the timing of the wobble of the Earth's axis of rotation. So I'm going to go through each one of these. The first one is eccentricity, and those are changes in the shape of the orbit that the Earth makes around the Sun. The Earth's actual orbit is not circular but slightly elliptical. The non-circular shape of the Earth's orbit is the result of the gravitational pull of other planets on the Earth as it moves through space. And the Earth's shape of its orbit varies from very low eccentricity, meaning it has a very circular orbit, to times of high eccentricity when it has a very elliptical orbit. And it takes about 100,000 years to go from a low eccentricity circular orbit to a high eccentricity elliptical orbit and then back to a low eccentricity orbit. So that's about 100,000 year cycle. And it varies from a pretty much round orbit with a eccentricity of 0.005 to high eccentricity about 0.06. And today we're at about 0.016. And at the farthest point from the sun, the Earth is 1.67% farther from the sun as during a circular orbit. So if we look at today's eccentricity 0.16 and we compare it to high eccentricity 0.06 and 0, we can see this is today, and the cycle has gone back and forth about every 100,000 years. So when there is a more elliptical orbit, so much more round orbit, the climate is slightly cooler because the Earth spends a significant amount of time away from the sun or further away from the sun. When the Earth has a more circular orbit, the climate is slightly warmer because the Earth spends more time relatively close to the sun. So an optimum for a glacial period would be times of high eccentricity, and to interglacial or warmer periods coincide with times of low eccentricity. So we are closer to times of low eccentricity, which partly explains why we have a slightly warmer climate. The next orbital parameter I want to go over is obliquity, and that is the tilt of the Earth's rotational axis. The Earth rotates on its axis that passes through the North and South Pole. This axis is currently tilted 23.5 degrees off of vertical. So you can see in the diagram, this is the vertical axis of rotation. Its present day tilt is 23.5 degrees, and it varies from about 21.5 degrees to 24.5 degrees. So remember, the hemisphere that points towards the sun receives more solar radiation and is warmer than the hemisphere that points away from the sun. As I mentioned in the last lecture, this tilt explains the seasons and why the northern and southern hemisphere experience opposite seasons. So summer heating is greater and winter cooling is greater when the tilt is high, more towards its maximum amount, 24.5. Summers are cooler when tilt angle is low, and that would enable persistence of year-round snow and is favored by cooler summers. So right now we're at 23.5 degrees, so we are closer to the maximum tilt, which is another reason why we are closer to an interglacial than a glacial time. So in general, when there's less tilt, there's less seasonal contrast, and that would create milder conditions. When there's maximum tilt, that would create more seasonal contrast and would indicate or cause warmer conditions. So keep in mind, this does not affect low latitudes that do not get affected by the tilt as much, but would affect polar regions. Therefore, this has a major influence on the glacial interglacial cycle because it amplifies or suppresses these seasonal differences which cause glacial times and interglacial times. So if you look where we are in this obliquity cycle, you can see there is a 41,000 year cycle between minimal tilt closer to the 22 degrees and the maximum tilt and then back down. So we are closer to the maximum tilt, which would indicate warm summers and would create closer to interglacial conditions. So remember in the last lecture when we talked about the equatorial regions receiving much more heat than the polar regions, and that getting redistributed by the atmospheric circulation and the ocean, which we call thermohaline circulation. It's this tilt that's responsible for this uneven heating or differential heating across our globe. The last orbital component, and probably the most difficult to understand, is called precession. And this is the Earth's wobbling motion. It's a wobble of the Earth's axis of rotation. It's caused by the gravitational pull of the sun and moon on the slight bulge in the Earth's diameter at the equator. The precession changes the timing of when the Earth is closer to the sun or further away from the sun. So the tilt angle is not changed, but the direction in which this tilts is. And this is a 23,000 year cycle. It's kind of like this spinning of a top. When it starts to slow down, it starts to wobble. That's not to suggest that the spinning of the Earth is slowing down, but it does have a wobble in terms of the direction that axial rotation is. So today the Earth rotates around an axis that points to the North Star, Polaris, but over time the wobbling motion has caused the axis of rotation to point to another celestial reference point. So the reason for this is that it's affected by Venus and Jupiter. So the North Star is where it's pointing now, and it has pointed to Vega over time. And this cycle of the wobble is on a 20,000 year cycle. The wobble of the Earth's rotational axis and also the wobble of its orbit involves complicated three-dimensional orbital motions in space, but they can be reduced to a simple concept, and that's basically which season is the Earth nearest to the sun. And we call that the Earth-Sun distance. And in a relative sense, is that distance large or small during the summer or the beginning of the summer, which we call June. So it's either more or less. This index is graphed here in this graph right there. If the distance, the Earth-Sun distance in June is less, that would encourage a warm summer and would favor warm interglacial conditions. If that Earth-Sun distance is more in June, the beginning of the summer, that would mean cooler summers, and that would favor more glacial conditions. So keep in mind, no one of these components of the Milankovitch cycle is enough to drastically alter climate. The differences are too small, too subtle. But when these cycles are in phase, the effect on climate can be greatly magnified. When these cycles are out of phase, about half the effect of each one of these cycles, and they can cancel each other out. So if you look at waves, for example, these two waves are in phase. The warm indicators of any one of these cycles can amplify that warming, and the cooling can amplify the cooling. So these are two different parameters that can be in phase at the same time. If they're out of phase, they would cancel each other out, or they can be slightly out of phase. But in general, what would cause a glaciation? It's when all three parameters are in phase, such as an elliptical orbit, a low tilt angle, and a high Earth-Sun distance in June. Conversely, if conditions were such that there was a circular orbit, high tilt, and small Earth-Sun distance in June, that would suggest warm conditions. So if we look at a climate record for the last 400,000 years, which you've already seen before, the Vostok core, you can see this is temperature anomalies, and this is 400,000 years ago. This is today. There have been variations in temperatures with highs and lows, highs and lows, highs and lows, high, low, and high. So if you notice, the warmings are very rapid, and the coolings are much more gradual, and we'll get into that later. But this has this sawtooth shape that's very typical of all the climate records of both hemispheres. But there is some pacing here. This is an actual record. This is not a modeled climate record. It almost seems too perfectly spaced. About every 100,000 years, there's a warm cycle. So what do you think, what part of the Milankovitch cycle is the drumbeat for this part of the climate record. It's the 100,000-year eccentricity record. That eccentricity record is very evident in most climate records of the last 800,000 years. So if you tease out any of the records, you will see a 41,000-year cycle, a 23,000-year cycle, but you will see the dominant cycle is that 100,000-year eccentricity cycle. And even if we extend the record back to 800,000 years, you see that same temperature record with that 100,000-year cycle. So most models suggest that these changes in orbital parameters are not enough to bring on the warmings and coolings that we've seen over the last 800,000 years. They are probably enough to start some coolings, but not enough to explain the great temperature variations that we've seen. So the idea is that there are certain things that have amplified these coolings and warmings, and these are called feedbacks. And I already mentioned some of these feedbacks. So if we look at global temperatures, so let's start with the global cooling due to the Milankovitch cycles, that would create a growth or an increase in ice sheets, which would now make more of the Earth's surface reflective, so it would change its albedo, creating more reflection, less absorption. That would then further bring down temperatures, which would then continue the cycle of bringing down the temperatures, creating an ice sheet, changing reflectivity, which brings down the temperatures. So you probably only need a reduction in summer insolation to start this feedback cycle. So remember, the summer insolation is the key, and the parameters that would indicate that would just start the glaciation, and then the system would kind of take off on itself. So this explains why we possibly got such cool times in the past, and it's not just the orbital parameters, but the feedbacks are related to that. So that concludes some of the most important natural forcings in climate change.